everyone, I'm Sung-Yu Kim in the School of Management Engineering at UNIST. Today I'm going to talk about two fundamental approaches in statistical inference. One is the frequentist inference and the other one is Bayesian inference. Let X indicate n independent draws from a probability distribution F. If X has taken a certain value, X, the value X is called the realization of X. For example, x1, x2 up to xn are n random variables from normal distribution theta and 1. Those random variables are also called a random sample. A realization has been observed, some numbers, and we want to infer some property of the unknown distribution F from observations. In this example, the unknown is theta. This is called statistical inference. Statistical inference consists in the use of statistics to draw conclusions about some unknown aspect of a population based on a random sample from that population. Statistical inference can be divided into two areas: estimation and hypothesis testing. In estimation, the goal is to describe an unknown aspect of a population. The goal of hypothesis testing is to decide which of two complementary statements about a population is true. Today we focus on estimation in this video clip. Estimation can be of two types: point estimation and interval estimation, depending on the goal of that application. Let me define a point estimator and point estimate. A point estimator is any function t of a sample. That is, any statistic is a point estimator, while an estimate is the realized value of an estimator. That is, observed when a sample is actually taken or realized. For example, we have a sample drawn from normal distribution theta and 1. We want to infer theta. We may consider a sample average as a point estimator of theta. Suppose that we have realized values for x1 to x10 like this, then a point estimate of theta is 2.047. The next question may arise: what is a good estimator and how to find it? But we will skip this question in this video clip. Now we are interested in the accuracy of the point estimate. We are curious about how accurate the value 2.047 is. And by definition of frequentist inference, the accuracy of the estimate is the probabilistic accuracy of uppercase theta hat as an estimator of theta. To understand it, imagine hypothetical random samples, first sample, second sample, and go on, generated by the same distribution, and we get corresponding uppercase theta 1, uppercase theta 2 using the point estimator. Theta hat is a realization of uppercase theta hat. Theta hat is just a single number, but uppercase theta hat takes on a range of values whose spread can define measures of accuracy. Conceptually, the accuracy of theta hat is based on hypothetical random samples. Let me explain this concept of frequentist inference in interval estimation. A confidence interval is a type of interval estimate computed from the statistics of the observed data that might contain the true value of an unknown population parameter. In other words, If confidence intervals are constructed using a given confidence level from an infinite number of independent sample statistics, the proportion of those intervals that contains the true value of the parameter will be equal to the confidence level. For example, a 95% confidence intervals for a population mean theta is this. What does that mean by the formula is a 95% confidence interval? Let us generate some hypothetical random samples of size n with the same probability distribution, normal, theta, and 1. For each sample, compute the confidence interval with the formula above. It is a 95% confidence interval because in 95% of the scenarios, the true theta lies in the confidence interval. In this figure, we generated hypothetical random samples of size n, and we plot all those confidence intervals in red when they do not contain the true theta. On the other hand, Bayesian inference requires one crucial assumption in addition to the probability family. That is the knowledge of prior density, G of mu, where G of mu represents prior information concerning the unknown parameter mu available before the observation of X. The Bayesian paradigm prescribes that the sample information be contained with the prior information using Bayes' rule to obtain the posterior distribution, which is update of the prior density G of mu after taking account of observation X. All inferences about mu are now based on the posterior distribution. For example, let X from normal distribution theta and sigma square, and suppose that the prior distribution of theta is normal distribution mu and tau square. Here we assume that sigma square, mu, and tau square are all known. The posterior distribution of theta can be computed easily. We skip its derivation here. The mean of posterior distribution, the posterior mean, is a point estimator of theta. We call it the Bayes estimator. The Bayes estimator is a linear combination of the prior and sample means. That means Bayes estimator takes advantage of both information sources. From the previous example, we can calculate the Bayes estimator given prior information. With the mean of obtained sample, we can calculate the Bayes estimate. In Bayesian statistics, we have a credible interval which can correspond to the confidence interval in frequentist statistics. A credible interval is an interval within which an observed parameter value falls with a particular probability. Formally, we can describe the credible interval as follows. And with the previous example, we can compute the 95% credible interval. We can see the fundamental difference between frequentist approach and Bayesian approach by comparing the confidence interval and the credible interval. A frequentist 95% confidence interval means that with a large number of repeated samples, 95% of such calculated confidence intervals would include the true value of the parameter. In frequentist term, the parameter is fixed and the confidence interval is random as it depends on the random sample, while a Bayesian 95% credible interval means that the interval covers the unobserved parameter with 95%. The parameter is not fixed. It has a distribution of possible values, and the credible interval is not random. It only depends on the already observed sample. Here are final remarks. Today, we talked about two fundamental approaches in statistical inference. We saw how they are different, especially in estimation, point estimation and interval estimation. This figure illustrates the difference of two approaches clearly. As shown in the figure, Bayesian inference proceeds vertically, with x fixed according to the posterior distribution g over mu given x, while frequentists reason horizontally, with mu fixed and x varies. Bayesian inference requires a prior distribution g over mu, while frequentism replaces the choice of prior with a choice of method, algorithm, or estimator. Having chosen g over mu, only a single probability distribution g over mu given x is in play for Bayesians, while frequentists must struggle to balance the behavior of t, the estimator, over a family of possible distributions, since mu is unknown. Today, the growing popularity of Bayesian applications reflect their simplicity of application and interpretation. Thank you.